Okay, first thing we're going to look at is how do you find the length of an arc of a circle? So it's really kind of asking, like, if you were walking along the edge of the circle, let me draw a little stick figure walking along the edge of the circle. La, 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 la. How far did they walk? So we want the length of that arc. Let's start with this. How do you find the distance to walk all the way around the circle and end up back where you started? How do you find that distance? And is there a name for that distance? When you first saw this word, you probably thought, whoa, hey. And it starts with a C. Begins with sir, but starts with a C. Circumference. Circumference. How do you find the circumference of a circle if you know the radius of the circle? Two pi r. Now, if 2 pi r is how much it takes to walk all the way around a circle, you can look at this arc length as being a percentage of the circle that you have walked on. And if you want to know how much of the circle you walked on as a percentage, you're looking at the angle divided by how much it takes to go all the way around. So if you take theta, the angle, and divide it by 2 pi, that is going to give you the percentage of the circle. If you then multiply that percent to your circumference, which is 2 pi r, you will find the arc length. But this formula is beautiful. Do you see? Do you see it? Arc length is the percent of the circle, which is theta divided by 2 pi, multiplied by the circumference 2 pi r, and yes, cancel. The 2 pi's cancel, and you are literally left with just theta times r. That's it. But very important, your angle must be in radians or this will be an incorrect formula. But this is why mathematicians like to use radians. So let's practice. Let's say you have an angle 3 pi over 2. And you know that the radius of the circle is 12 feet. If you want to find the length of the arc, all you have to do is multiply those two numbers. And then just to point out, you've got divided by 2 times 12. And so that gives you 18 pi as an answer. And if you want to use your calculator for that, you can as well. So now everybody try this next one. Can you find the length of the arc? And just to make sure you're clear, this arc, what is its length? And type it into chat when you've got it. I don't have it in decimal form. So let me see if that's correct. And I'm trying to find my pi button, and I am blind right now. Okay. I'm not getting that. So basically, come on. Work for me, pen, work. You're multiplying 19 pi over 12 and the number 6. So we end up getting 19 pi divided by 2. As a decimal number, that's going to come out as 29.845. You can leave the answer this way, though. And that's arc length. 114. Oh, okay. I just simplified the fraction. You should have the same answer. Let me double check. 19 times 6, 114. You should, yeah, from that, you should be getting the 29.845. Check how you put it in your calculator. You might have typed a wrong number somewhere. And actually, did you remember to type the pi? Oh, yep, there we go. That's it. Okay. Now, we're going to do a lot more with applications in this unit. And the first application we're going to look at is circular motion. So I have a question for you. Why would anyone want to put larger tires on their cars? Give me some reasons of why someone would want their car to have larger tires, or maybe I should say truck. It does work. Short people cannot get into their car easily. What are some advantages with having larger tires? Yeah. I think that's a lot of people. More rubber to burn. Can someone think of what you get out of it with bigger tires? Mileage, yes. Why do you get better miles per gallon? If the tires are bigger, how do they give you better miles per gallon? I happen to have some things ready. Right. Same RPM, different distance. And RPM, if you don't know, means revolutions per minute. And I'm trying to remember. First of all, no. Actually, I wanted to do this one first. Okay. What I'm going to do is on one of these circles, I'm going to change the radius Let's change this one. So now I've got a larger radius, and I'm going to animate this and just watch it go around. But now I'm going to show you where they are together. So they're superimposed now. I want you to think about the distance you are traveling with smaller tires versus bigger tires. In one revolution, you will only go a distance of your circumference. So this is showing you a rolling wheel and the distance that it covers for every rotation is the length of its circumference. And I've got a few of these just for fun. Here's a fun wagon wheel. Whee! That just only did half a rotation, and you went, it's a radius of 1 unit, so you went only pi of a distance. And let me get back over here to the notes. So you want to understand then the difference between angular speed and linear speed. Angular speed is how quickly the angle is turning. That's where you're going to be looking at things like revolutions per minute. Revolutions per minute is an angular speed. And I'm going to grab the answers because they're nicely. So angular speed is usually designated by this Greek symbol, omega. And it is just looking at how much did you turn and dividing it by how much time passed. If you want to know your speed, you need to take how much occurred and divide it by time. So if you want to know your angular speed, you take the angle that was swept and divide it by the time. And, whoops, wrong one. Wrong one completely. There we go. Back over to here. Then what I want to do is take you over to example 2. Can the angle be greater than? Yes. Yes, it can. Because you're just, if you have one rotation, then your angle is 2 pi. If you have more than one rotation, just keep adding. Let's take a look at example 2 just to find angular speed. An object sweeps out a central angle of pi over 3 radians. So basically, what that is saying is you are turning a pi over 3 angular amount. And the radius of that circle is 3 meters. Now, if you think about it, the angular speed is actually, we have 10 minutes. We have 10 minutes left. You could look at the length of your arc divided by the amount of time, your angular speed. Actually, no, wait, I'm sorry. I said that wrong. Your angular speed is looking at how much did you turn and dividing that by how much time took place. And the time is 0.5 seconds. So what is pi over 3 divided by 0.5? 2 pi over 3, and you can write it as a decimal number as well. So that's the angular speed. It just lets you know how quickly it's rotating. Now, let's go back up and talk about linear speed, because you want to understand that linear speed is just looking at, say, the speed of your car. So I want to go back over to these. Linear speed is how quickly are you moving horizontally while you are turning. And that's where you're actually looking at the arc length divided by the time. So linear speed is your arc length divided by time. Because what is speed? Speed is distance divided by time. So if you want to know the speed you are traveling horizontally, you need to know the arc length and divide that by time. And the arc length, what is the arc length? What did we just find out was arc length? What formula is arc length? Okay, it doesn't want to move right now. There we go. Yes. Arc length is theta times r, the angle multiplied by the radius, and then divided by time. Now, one thing that is helpful is to realize that if your angular speed is theta divided by time, then you can look at your linear speed as being the radius multiplied by the angular speed. So over here in the answers, the first formula here is showing arc length divided by time. Often we use the letter S for arc length. And so we end up getting the formula r times theta over t, but realize that another formula is, let me shrink that down, the radius multiplied by the angular speed. So if you know the angular speed and you want to know the linear speed, all you have to do is multiply by the radius, and you have it. So then if I come back over to the problem, where did it go? Example 2. If I come back over here to example 2, if I found that my angular speed is 2 pi over 3, then to find my linear speed, all I need to do is multiply 2 pi over 3 by the radius. And so in this case, the linear speed is 2 pi. Now, let me come back over here. So when we bring in the units with it, if you think about angular speed, the units that we speak of when we speak of angles are radians right now. However, it could have been degrees, but then we would need a different formula. And then over some unit of time, in this case, it's seconds. So the angular speed ends up being 2.09 radians per second. The linear speed Now, if you think about it, does it make sense that when you're driving a car or bicycle and you ask what is your speed, you're going to give something like miles per hour, meters per second. And I want you to notice that even though we say radians per second when we're talking about angular speed, we actually ignore that radian unit when we look at the units for linear speed. How would you put the equation into the calculator? You can do pi divided by 3, push enter, and then divided by 0.5. But when we talk about application problems, units become very, very important. When you do your science classes, you always have to put units because that makes a big difference. So what I want you to begin to understand is that technically, angles don't have a unit that it is measured in, because an angle is just looking at how much did you turn. That's it. If you look at the formula for arc length, going back. If you look at the formula for arc length is right here given by the letter S. S is a distance. The radius is also a distance. With that in mind, your angle is actually a ratio of your arc length to your radius. Now, let's say you're using the metric system. Then arc length is going to be a certain number of meters. And then your radius is also a certain number of meters. If you're looking at a ratio of two identical units, those units are going to cancel out. And that's why technically an angle doesn't have a unit of measure. We say radians more as a placeholder, because another way we could say it is how many rotations were made. And anyway, so what did I want to say next? Now I remember. You want to make sure you understand that angular speed describes how fast something is turning, and it does not matter how big the circle is. Linear speed is affected by how big the circle is, and it's based on how far a circle has traveled while it is turning. And I'll keep that up for a minute, and then I'll show you the fun little GIFs that I found again. Actually, let's see if I can put that in part of it. And there. So angular speed is just how quickly is it turning, but the linear speed is this actual distance divided by time. And then I just have this diagram here to emphasize how quickly the turning goes. That is your angular speed, but how quickly it moves along is your linear speed. To give you, I have this picture for your classwork to give you a visual picture of the meaning of angular speed and linear speed. Oh, class is over. You want to know, though, what is due tonight. I knew I wasn't going to finish this classwork, so I'm going to have to give you an extra day on the classwork and the homework. However much you get done today, you don't have to do tomorrow. What is due today, though, are the answers to homework 7.1. So make sure you remember everything we learned from 7.1 and get that turned in. You made it through day 1. Oh, and I stopped recording. I almost forgot.